Hey there, and welcome. Today, we're going to pull back the curtain on some hidden chemistry that's literally everywhere, in your kitchen, inside your body, and even in something like a bee sting. We're talking about acids, bases, and salts. You know, the invisible forces behind so many of the things we experience every day.
So, let's start with a really simple question. Have you ever really stopped to think about why a lemon tastes so sharp and sour, but a little bit of baking soda has that kind of bitter taste? The answer? Well, it's not just about taste. It's pure chemistry, and we are about to break it all down.
All right, here's what we've got on tap. First, we'll figure out what acids and bases even are. Then, we'll look at what happens when they react. We'll get into the power of pH, see how this all shows up in your daily life, and finally, we'll uncover the secret world of salts. Sound good? Let's go.
Okay, so let's jump right in. Our story really begins with the two main players on this chemical stage, acids and bases.
So on a basic level, how can you tell them apart? Well, acids, like the stuff in vinegar or lemon juice, they're the ones that taste sour. Bases, on the other hand, like baking soda or even soap, they tend to taste bitter and feel kind of slippery. And hey, a huge disclaimer here. We are not telling you to go around tasting random chemicals. That is a very, very bad idea. That's why scientists use things called indicators. The most famous one is litmus paper. Acids turn it red and bases turn it blue. Simple as that.
These indicators are basically our chemical detective tools. They give us these really clear color clues. You can see litmus is the classic red for acid, blue for base. But look at methyl orange. It also turns red in acid, but goes yellow in a base. And phenolphthalein? That one's even cooler. It's totally colorless in an acid, but the moment it hits a base, bam, it turns this brilliant bright pink.
So what's actually going on at the tiny molecular level? Well, the Arrhenius Theory gives us a fantastic explanation. It basically says that an acid is anything that releases hydrogen ions, that's the H+ you see there, when you dissolve it in water. And a base, that's anything that releases hydroxide ions, or OH-. This one little difference is the key to everything. So that sour lemon taste, you're tasting H+ ions. That bitter baking soda, that's the OH- ions at work.
Okay, so we've met our main characters. Now, what happens when they actually interact? This is where things get really interesting. You know, when an acid and a base get together, they perform this amazing chemical balancing act. It's called a neutralization reaction. The H+ from the acid and the OH- from the base are drawn together like magnets, and they form water, just plain old H2O. And what's left over combines to make something called a salt. They literally cancel each other out, creating something totally neutral. Acids also do some pretty cool things with metals. Check this out. If you take an acid, like sulfuric acid, and add it to a metal like zinc, you'll see it start bubbling. That's hydrogen gas. And there's a classic test to prove it. You trap that gas in soap bubbles, bring a lit candle close, and you get this awesome, distinctive pop sound. It's the signature sound of hydrogen. Now, it's really important to know that not all acids or bases are created equal. Some are incredibly strong, and others are pretty weak. So how do we measure that strength? For that, we need a universal scale, and that's where the power of pH comes in. The pH scale is super straightforward. It runs from 0 all the way up to 14. Anything below 7 is acidic. Anything above 7 is basic, which is also called alkaline. And the further away you get from the middle, the stronger it is. So a pH of 1 is way more acidic than a pH of 6. And right smack in the middle, that's our magic number, pH 7. This is the point of perfect neutrality. Think of pure water. It's not an acid. It's not a base. It's the perfect balance point for the entire scale. Okay, so H+ ions, pH scales. Why does any of this actually matter to you? Well, it matters because this chemistry is happening all around you and even inside you every single second of every day. Let's see why this is so important. Your stomach, for example, is filled with super strong hydrochloric acid to break down your food. In your mouth, if the pH drops below 5.5 because of sugar, the acid that bacteria produce starts to eat away at your teeth, causing cavities. That painful sting from a bee, that's an injection of methanoic acid. And on a bigger scale, when rain's pH drops below 5.6, we call it acid rain, and it can cause all sorts of problems for the environment. And this leads to a perfect everyday example of putting this knowledge to use. Ever wonder why toothpaste works? It's because it's usually basic.
So when you brush your teeth, you're actually performing one of those neutralization reactions right there in your mouth to fight off all that cavity-causing acid. Pretty cool, right? So we mentioned that when an acid and a base neutralize, you get water and a salt. But when chemists say salt, they're not just talking about the stuff you put on your fries. The world of salts is way more diverse and way more interesting than you might think.
One of the most fascinating things about some salt is that they can trap water molecules right inside their crystal structure. It's called the water of crystallization. A great example is copper sulfate. It holds on to 5 water molecules for every 1 unit of the salt. And it's that trapped water that gives it this beautiful, vibrant blue color.
And this idea has a huge real-world application you've probably seen before. Plaster of Paris starts as a powder because it has very little water trapped in it. But when a doctor mixes it with water to make a cast for a broken bone, it sucks up that water and rehydrates, turning into a different salt called gypsum. That chemical reaction is what makes it turn into a hard, solid mass that keeps her bone in place. And of course, we can't forget the salt that everybody knows, sodium chloride, or just common table salt. It is so much more than a seasoning. It's a fundamental raw material for the chemical industry, used to make tons of other important things like caustic soda, baking soda, washing soda, even bleaching powder. It's a true cornerstone of modern chemistry.
So there you have it. From the sour pucker of a lemon to how your toothpaste works to how a broken arm is set, it's all about acids, bases, and salts. The next time you're in the kitchen or just going about your day, remember that you're surrounded by this amazing chemistry. You're practically a chemist yourself. So the question is, what are you going to look at differently now?